Okay. We're back with the second part of chapter 2. So in the last lecture, we stopped after we talked about radioactive isotopes. And now we're going to talk about a different kind of non-standard, non-typical atom. Screen share here. And like I said in the last lecture as well, it also starts with an I. And they are called ions. Okay. All right, so let's continue. Ion is a positively or negatively charged. Okay. So you remember how I said that, like with carbon, you have 6 protons, 6 neutrons, 6 electrons. There's no charge on that atom because the positive and the negative charges cancel each other out. In ions, the positive and negative charges don't cancel each other out because they're not equal. They're not equal because we don't have the same number of protons and electrons. Okay. All right, let's talk about how this works. I'm going to start with sodium. Okay. Remember that sodium has an atomic number of 11. Okay, so protons, neutrons, electrons. So how many protons for sodium? 11. Neutrons, 11. Electrons, 11, because this is our standard atom. But sodium can become a positive ion, meaning it has a charge on it, a positive charge. Okay, now we're going to do how this works out. All right, let's look at protons. How many protons should I have in sodium? Got to look at an image here of something. Okay, so what are our thoughts on atomic number for sodium? Because we know it has a positive charge on it for the sodium ion. So what does that mean? Well, sorry, I can't look for the specific image, and I could find it on my phone when I Googled it, but I can't find it when I pull it up on my internet, Google, and I do not understand why that is, but I find it frustrating. So I was trying to find it again, but I can't. So moving on. Okay. Sodium ions still have 11 protons. Why is that? I know, because all the sodium atoms in the entire universe have 11 protons. That's right. How is it possible to have 11 protons still, but a positive charge? Feels like we should be adding protons, right? Well, we can't, because if we were to add a proton, we would end up with magnesium, because then we'd have an atomic number of 12 if we added a proton. Well, atoms that have an atomic number of 12 are magnesium. So obviously that can't be the answer. This is an ion, not an isotope. So we know we're going to have still 11 neutrons. So now we only have one option. Where are we going to get our positive charge from? It's going to be the electrons, right? You can't add an electron, because if I add an electron, that's going to give this a negative charge, because there'll be more electrons than protons. So I actually have to take away an electron here. So instead of having 11, sodium ions have 10, okay? 10 electrons, which means there's one extra proton than electron and gives this a positive charge, okay? It's another one we could do. Let's do calcium. Let me put this, okay, so our calcium has an atomic number of, I don't have this one memorized, so I'm gonna have to look this one up real quick. Calcium is 20. All right, calcium also becomes a positive ion, but first let's start with our typical. Okay, so we have how many protons? Atomic number of 20, 20 protons, 20 neutrons, 20 electrons, because this is a standard atom. But calcium can become a 2+, also written. Okay, so then we have, let's do this for 2+, protons, neutrons, and electrons. We already know it can't be the protons, because if we add one, it becomes a different element. So we're going to do protons is 20, neutrons is 20. What about electrons? This is a 2+. It means it has 2 positive charges, which means it has 2 more protons than electrons. So we're looking at 18. Make sense? Let's do negatives. I don't want to erase everything I've got. It's always part of it. All right, I'll leave this as a positive. Let's do chlorine. It's an atomic number of 17. Okay, so now we'll do our normal atom, protons, neutrons, and electrons. All right, so just double check my image here. Protons, we have 17, right? Neutrons, 17. What about electrons? This is a standard atom, so we have 17. Well, chlorine, unlike sodium, becomes a negative ion. Okay, so this is just Cl. Cl. This is Cl minus, or a negative ion. So what do we have? Protons, neutrons, electrons. I'm not even going to ask about the protons. We already know it's got to be 17. Neutrons have to be 17. Electrons, in order to have a negative charge, that means we have to have one more electron than proton. So now this is going to be 18. Okay. All right, so this takes me to my next part of the lecture, which is on chemical bonds. Move the things, get the thing. I miss teaching in class. I'm not gonna lie, because then like the stuff was just there and I could write on the board and I could see your faces and I would know if you were like confused or if you were crying or if you hated me, because I could see it. And now I'm just like talking to myself in a room alone and have all this crap that I'm constantly trying to get out of the way. Anyway, I digress. Let's move on. All right, let's talk about chemical bonds. Circle back around to our ions here in just a second. So chemical bonds are formed because of the attraction between atoms. So let me reword how I said that. Chemical bonds are the attraction between atoms that hold those atoms together. okay? Hold them together like in water, which we already talked about, H2O, right? Well, something has to hold those two hydrogens to the oxygen. And I kind of drew that picture for you. And what you can see is that it's the electrons that interact with each other. And the electrons then are the ones that are responsible for chemical bonds. Okay? So it's the electrons that do that. Responsible, I can do it. Okay, let's talk about the three different types of bonds. First one is covalent. Covalent bonds are the strongest type of bond that we'll talk about, really the strongest type of bond. And you can think about electrons. It's part of what makes it strong, because both atoms get what they need by sharing with each other. Okay? The second type of bond is an ionic bond. I can type on the right home keys. All right. Ionic bonds. Ionic bonds are a bond that's formed between, surprise, ions. Because it's direct. Okay. In ionic bonds, rather than being shared, kind of think about those electrons being transferred. Okay. I'll get into this a little bit more in a second. Finally, we have hydrogen bonds. Hydrogen bonds are formed because of the weak attractions that exist between neighboring water molecules. I'll get into this in a minute. All right, so let's look first at ionic bonds, because that's what I have sitting up here on the board at the moment. Okay, so I have a sodium ion with a positive charge, and I have a chlorine ion with a negative charge. What happens when I add those together? I get a compound called sodium chloride. Anybody know what that is in everyday English? It's table salt. Okay, stuff you can use as flavoring. That's what NaCl is. Notice that sodium chloride, salt, doesn't have a charge on it. And that's because the positive charge from the sodium and the negative charge from the chlorine cancel out in the whole molecule. Okay, so salt itself has no charge. Now, I must take a slight detour here, because I'm going to show you how to read chemical equations, because that's what this is that I just did. What color shall I do? We'll just do this. All right, so first off, what you can see here is I've got my reactants. So the things that go into an equation are called reactants. And this is on the quiz, okay? And then the thing that comes out of the equation is the product, or products. Because a lot of times in chemical equations and in chemical reactions, you have multiple reactants and multiple products. Sometimes you have a single reactant and multiple products, but you need to know what these terms are, okay? So I have my reactants showing that I'm doing sodium plus chlorine, the ions, and then we use this arrow. And in chemistry, when you're writing equations, you don't use an equal sign. like you do in math. Instead, you use an arrow like this, and this arrow means yields. This is what you get out of it. Okay. So if I were to say this out loud, I would say sodium ion plus a chloride ion yields sodium chloride. Okay. That's just so that you know what the terms are. All right. So what happens here in this ionic bond is that, I'm not going to draw it all out for you because you don't need to know. If you're interested, I'll tell you. But what happens is, remember how sodium is missing an electron and how chlorine gains an electron? Well, guess what? The electron from here gets transferred to here. Okay, that's how they are a transfer of electrons, if you will. Really, that means that the electron that should have been hanging out with sodium is now hanging out with the chlorine. Okay, so sodium gives one up and sends it to chlorine. And that's what happens in all of these ionic bonds, is that one atom is giving up one or more electrons to another atom. Okay. All right. So this is an ionic bond. Okay. In a covalent bond, like water, you have a covalent bond. So the hydrogen atoms are sharing their electrons equally with the oxygen. So hydrogen isn't just giving it away and transferring it and becoming, you know, an ion. It's sharing with oxygen. Everybody has their needs met. Everybody's happy. This is a covalent bond. Okay. All right. Let's continue. Again, for your notes, reactants are what go into an equation, products are what come out. Okay. All righty. What else am I going to share? We're going to go over the last part of chapter 2, which talks about the life-giving properties of water, and there are 4 of them. So yes, this is chemistry because these properties come because of chemical interactions. Okay, so the four life-supporting number 1. First thing is something called cohesion. Cohesion is basically allowing molecules to stick together, to stay together, right? Okay. The cool thing about cohesion is it lets plants defy gravity. You ever thought about that? When you water a plant, where are you supposed to water it? At the top, and then it goes down? You water plants at the roots, right? And then the water goes against gravity by moving up. So you water even the biggest tree is going to take in its water at the roots, and then it travels all the way to the top. That's because of cohesion. So one water molecule likes to hold on to the other water molecule, and then there's one holding on to that, right? You got this chain of water molecules, and they all kind of end up pulling each other up through some of these other processes in a plant that allow movement of nutrients. But the fact that those water molecules hold together cohesively allows it to keep moving in an unbroken chain. It's the same type of reason that water moves up a straw, right? Or a water-based liquid will move up a straw. You have the vacuum force that's created like when you seal your mouth over the straw and suck upwards, but the cohesion property of that water-based liquid allows not just one molecule of that liquid to get into your mouth, but a bunch of it because they're all hooked together. Okay, cohesion is not the same thing as a chemical bond. It's just that we're all the same type of molecule, we should all stick together, that type of thing. One of the ways they say this is water goes from roots to shoots. In other words, bottom to top, okay? Cohesion has this other property called surface tension. Surface tension is super similar, except this is specifically a measure how hard it is to stretch the surface of a liquid. Basically meaning how far can you stretch it before it separates until that cohesion is broken. Water has high cohesion and high surface tension, meaning it loves to stick together and it stretches quite a bit. This is why those little like water bugs can stand on the water, okay? Their mass isn't enough to disrupt those cohesive properties, okay? So they don't fall through the water, they can stand on it. All right. Actually, I'm going to say, where's my little, so water has high cohesion and strong surface. Why is this a life-supporting property? Again, we kind of need plants. We kind of need primary producers. And if we couldn't get the water from the roots to the rest of the plant, it wouldn't grow. That's just one reason why cohesion is life-supporting. All right, next we have temperature moderation. Water does an incredibly good job at holding on to its temperature, holding on to its heat, okay? That's long. Water stores a lot of energy, so it can take on a lot of heat before the temperature rises. And that's because of those hydrogen bonds we talked about. Now I'm going to kind of show you how they work. All right, so I'm going to have my water molecules here. And water molecules actually are kind of shaped like this. It's the way that the hydrogen bonds to the oxygen. They're called bond angles. Anyway, so this is a molecule of hydrogen. Actually, I'm gonna do this different. I can do this. Okay, hydrogen, oxygen, hydrogen. I'm going to show you different kinds of bonds here. So ignore that, I'll fix it in a second. Bear with me. Hang in for just a sec for me. Okay, these black lines represent covalent bonds. Okay, so you'll notice that the hydrogens and water are covalently bonded to the oxygen. Remember, sharing. Well, what about hydrogen bonds? Here they come. Hydrogen bonds are these weak attractions between the oxygen of one water molecule and the hydrogen of another. And that's because water is a polar molecule. Yep, you need to know this too. A polar molecule has partial charges. Okay, they're not ions. They don't have a charge like sodium or chloride. The whole molecule itself will have a partial charge. So oxygen, having more electrons, let's do this sign backwards, has a partial negative charge, and the hydrogens have a partial positive charge. Okay. The whole molecule is balanced because it's partially positive on one end and partially negative on the other end. But these charges make water molecules super attractive to each other. Okay, because here I've got my hydrogen from this water molecule and it's positive. It's like, hey, oxygen, you're looking pretty negative today. I like it. So it's attracted to this oxygen and the oxygen is like, back at you. You're looking pretty positive. How you doing? I don't know. This is their pickup line conversation in my head. And so because they're attracted to each other with this charge, partial charge, they form a hydrogen bond. Okay, the attraction between one water molecule and another. So here we go again with another water molecule to this one. Got this going on here. We got this going on here. And again, my dashed lines, these are hydrogen bonds. Okay. All right, so pretty soon you can see that we'd have kind of this web almost of water molecules. Just going to add in another couple so we can kind of see how that might work. Okay, so you can kind of see how you get this interconnected web of hydrogens from one water molecule being attracted to the oxygens of another. These hydrogen bonds, this is why water's cohesive. Okay, it's because it's attracted to each other. One molecule is attracted to the other so that when everything moves up in a straw or up the tree, they're all still holding on, right? Because how you doing? The polar molecule and the fact that these hydrogen bonds happen, again, are also the reason why water holds on to heat for so long. Have you boiled water before? I'm going to assume that your answer is yes, that you've boiled water before. In which case you'll note that you can put water in a pot, turn it on high heat, and then you stand there and wait. That's because that's a lot of heat you're adding to it. But we have these hydrogen bonds here. And the hydrogen bonds are holding all of this liquid water together, right? And it takes a lot of energy to break the hydrogen bonds. Where does that energy come from? Well, it comes from the heat that you're putting in, right? When water takes on enough heat, it will break these hydrogen bonds. Okay, when the hydrogen bonds are broken, it allows water to change states from your liquid to a gas, right? That's why when water does start to boil, steam starts to come off, because that water is changing from its liquid state to its gas state as the temperature increases. In case you're curious about how heat causes this to happen, causes water molecules to break apart, to break those hydrogen bonds. It's kind of basic, but hydrogen bonds keep water flexible but stable, right? Water molecules still hang together even when there's movement. Well, as you add heat to water, or really to any system, the movement of those molecules becomes a little more rapid and a little more out of control. Okay, as you add more and more heat, those molecules get more and more jittery, the movements become more and more chaotic, and that movement finally severs that bond, that attraction, because there's simply too much chaos for the bonds to hold the molecules together. Okay. All right. That was fun. I enjoyed that. Did you enjoy that? Let's move on to number 3, shall we? Number 3, floating ice. Yep. Floating ice is essential for life. Oh, temperature moderation. By the way, the fact that we have such large bodies of water on this planet mean that we can keep our temperature across the earth fairly stable. Different regions have a normal range of temperatures, and that's all because it takes so much to heat up water. It's one of the ways that they use to identify how much global warming is happening, because if you can heat up entire bodies of water, you figure that we are increasing the heat that's trapped in the atmosphere. Having said that, we go through, I say we, the Earth has gone through periods of fluctuation between heat and cold, and melting ice caps and freezing ice caps ever since it first came into being. Yes, humans do contribute to that. The debate, of course, is how much do humans really contribute? But the temperature moderation thing is, again, one of the things they use to help kind of determine what's happening with climate change. Okay, floating ice. Cool thing about water is water molecules move apart. They move away from each other. Temperatures drop. Okay, so when we add the heat, they speed up and break apart. But when we lower the temperature, the movement in those molecules, even the ones that's like the fluid movement and liquid, they slow way down. And as they slow down, those water molecules move farther away from each other. Okay, when they move farther away from each other, it becomes less dense. Okay, so we have frozen water is less dense than solid, or than liquid water. So frozen or solid. We don't think about this very often because it just is, but honestly, how many solids can you put into a liquid and have it float on the top? Nothing. Not really. There are some chemical things that can do that, but just in everyday life, maybe if it's hollow, if it's filled with air, then it will, but that's not really solid all the way through. Solid things usually sink, but not with ice. Okay, this is important because ponds don't freeze from the bottom up. If they did, all the stuff that was alive in it would be dead. So after winter and the temperatures return to normal, there'd be nothing in our fresh water sources that had any life at all. Everything would be dead. It would kill off entire ecosystems. And even assuming that you could put living things back in it during the warmer months, when it froze, it would just freeze from the bottom up again and kill everything. That's not an efficient way to live, right? Kind of defeats the purpose of living, in fact. So the fact that ice floats means that in fresh bodies of water, ice stays at the surface, and all the things that are alive can live underneath it. The ice actually serves as a bit of a blanket even for the water and the organisms that are below it, and that it keeps the temperature of that water consistent. It's really pretty awesome. This is also due to hydrogen bonds. Bring it at you. Okay, so think about those hydrogen bonds I drew with the dashed lines. Think about those spreading out. Everything's kind of at arm's length, forms this crystal lattice type thing. Okay, last one. This is water's solvent capacities. Basically, water's really good at dissolving things. There you go. If you're looking for a super scientific explanation, you're disappointed because I didn't give you one. But this is why. It's really good at dissolving things. Now for the super scientific part, it's because of water's polar nature that it's so good at dissolving things. Because if you think about it, remember how oxygen has that partial negative charge and hydrogen has the partial positive, and they like to hang out together because of that? Well, guess what? There's a lot of other things that also like to hang out. For instance, if you add salt to water, what happens? Those salt crystals disappear. They dissolve, right? That's because the positively charged sodium is super attracted to that negatively charged oxygen, partially negative, right? And the negative charged chloride ions, super attracted to that partial positive charge of the hydrogen. It breaks it apart, it dissolves it. So water is good at doing that with a lot of different substances for that reason. So there's your scientific part. Okay. I will ask questions about all of these things. So kind of do your best to understand how the hydrogen bonds play a part in these properties of water, how polar nature, the polarity of water plays a part, and kind of what's so important about hydrogen bonds, why they keep water temperature stable. Remember, it's the energy it takes to break them apart. And then obviously vocabulary, lots of vocabulary. And I will probably ask you to identify the number of electrons or the number of neutrons in different atoms. So I might give you an isotope and ask you how many neutrons it has, or an electron, an ion, and ask you how many electrons it has. And of course, I'd give you all the information that you needed, like the atomic number, to be able to answer that. Okay. If you have questions, please reach out to me. Let me know. And I'll be happy to go over this with you because, again, you're not the only one with questions. Okay. I will talk to you guys in chapter 3.